deep learning works. But before that, let me tell you a bit about Metis. Metis is the data science training home, and you get skilled, you get connected, and you get hired. And that describes our boot camp, essentially, which is an intense 12-week experience, and it's a lot of fun for those who like that. And for those who prefer, there are also evening classes that cover aspects of data science. So with that, let me get on with why deep learning works. And the short answer is I don't know. But that's why I started looking. Okay? So I'll take you through what is deep learning roughly, reasonably quickly, and maybe point you at some references that might take you further. The feed-forward step, and then how you do backpropagation to learn. And then we start looking at questions about why deep learning works. It works immensely well. I've been building simple models with Keras and so on, and they're just so easy to put together, and you get really good, strong models. And the method seems so simple, so it's really puzzling. Why does it work so well? Shouldn't it be caught somewhere in some complex optimization minimum? And instead, you get good answers. So we look at the energy landscape, which is starting to explain why it might work. Then we'll look at another approach by some physicists, tying it to the Renormalization Group, which helped explain phase transitions. We'll see how that goes. And then there's some more recent work which sort of describes the flow of the learning process by Tishby and associates. So we'll look at that as well. So there's three different perspectives, right? None is guaranteed to be right. They explain different features of the problem, and we'll take it from there. So what is deep learning? We'll look roughly at a feed-forward network, meaning all connections are forwarded to the next layer, right? The layers, nodes built into a layer, and they all connect forward. And we typically look at fully connected layers where each node is connected to every node in the previous layer. It simplifies some of the mechanics. So there's a bunch of inputs xi coming in at the top in what's called the input layer. And each of these hidden layers has a bunch of weights that operate on the xi's. It's a linear or affine transformation. And then there are these nonlinear activation functions that come in, right? And that nonlinearity turns out to be essential to learn complex boundaries and things like that. And basically that nonlinearity applies to the linear operation on the x's. And the deep just means that there are many hidden layers. That's deep learning. In one slide. The activation functions typically look like, we saw the logistic sigmoid represented in the previous slide. There's another tanh which goes from -1 to +1 at plus infinity. There are some more recent ones that are easier to compute with, right? And they have roughly the same behavior. The point is that the sigmoid and tanh functions, because of the nonlinearities, are harder to compute. And they also tend to saturate, so that saturation causes problems where the network sort of sits and does nothing. So people experiment with introducing different kinds of activation functions. And these are some of those that were tried. So the first step of the network is to set the inputs, right? And then take typically a small batch of inputs and apply random weights throughout the system, randomize the weights at all the nodes, the W's that we saw. And then what they do is they apply the weights, the equations that we saw at each layer, and compute forward, right? So given an input, you can compute the result of applying those random weights and the activations all the way forward, right? And then when you reach the end of the network layer, the output layer, what you do is then you compute either a classification or regression error at that point. Right? And now our purpose so far is we've set an input and computed an error. Now we want to go back and see how that error can be reduced. How should we modify the weights to reduce the error? And that's the major learning step, which and that's, oops, my slides got too big. So yeah, this slide sort of steps through the loss computation, which is essentially when you apply the weights and apply the weights on the input and include the biases and then apply a sigmoid to them. You end up here. And after that, you compute the probabilities using a softmax function. And in this case, what happened is you're dealing with a 3-class problem here. And the correct class happens to be a blue, so it sort of guessed wrong. The highest probability should have been a green. So you get a sort of higher loss in this case. So once we have the loss, we try and figure out how we take that loss and backpropagate it to figure out how to adjust each of the weights. And the basic process is simply that starting at the end, at the output layer, you have the loss computation. You can see that this error depends on whatever is defined in this layer. So if I take all the weights in this layer, I can completely represent the change in this error. And similarly with any of the layers, if I want to determine how this particular weight impacts this layer, all I have to do is introduce its derivative with respect to all the layers along the way, right? So what you do essentially is compute the gradient of this loss function with respect to each of the weights in each of the layers using the derivative chain rule. Once you have the derivative, you have to figure out, how you take a step in that direction, how big your step should be. And there are a number of ways of figuring that out. Essentially, they all stem from gradient descent of some sort, where the aim is you compute the gradient and you take a step in the direction opposite to that of the gradient. This is a slide that shows a number of different optimizers that are used. And they perform differently, some faster than others. And the whole aim is to get quick convergence. So then we get into asking, what does the loss function landscape look like? Which is, why does gradient descent work? Why doesn't it get stuck in all these valleys that arise in the landscape of the deep learning problem? There are so many weights, and all of them interacting through nonlinearities. We would get some complex surface like that. Why don't we get stuck? Why do we get good answers? A few people have looked at this. One way of looking at it is, since the space is too complex to take in, right? The idea that Ian Goodfellow and colleagues had was to look at a linear path from the starting point to the ending point, right? And look at all the non-convexities and things that happen along the path, right? And when they did that, they found typically that the path was pretty smooth. If you take the starting set of weights, say W initials, and then you run it through the training through a bunch of epochs, backpropagation and so on, and you arrive at an ending set of weights, W final, and then you plot a linear path from W initial to W final, right? They found that it was pretty smooth. So the question then was, what's happening? I mean, you can see that if you plot the actual gradient path outside the linear path, it sort of wobbles, but it sort of stays close to the main linear fold from the beginning to end. So then they looked at the training and validation error on, this happens to be on the MNIST data set with max out. And what they found was that the linear interpolation that they did, right, gets the energies very close to the full gradient descent. Right? Except, of course, that after a certain point it takes off. Right? So the basic idea here is that when you start training, you see some non-convexity at the beginning. But after that initial period, it looks like a normal convex function. And you're descending, easily without hills and valleys, or so it seems. So that was a big find. And they've tried this with different models and found similar results with some variations. So they have some theoretical backing as well that was developed earlier with spin glass models and so on. And so their experiments sort of confirm the earlier ansatses that there are saddle points at high values of the cost function. I mean, the cost function is, I guess, very high dimensional. So if you have some kind of an optimum, the odds are it's a saddle point, right? Because, I mean, for a minimum, you need all the curvatures to be like positive. For a maximum, you need all the curvatures to be negative. With so many dimensions and so many curvatures involved, the odds are you'll get some kind of saddle point, right? And that turns out to be true at high energies and sort of less so at low energies. Because in low energies, you have to have the right curvature to be a low energy. So what they found was that the minima tend to lie at low values of J that are close to the global minimum in a few different model experiments. And these minima turn out to be pretty good and had pretty good test error. So the reason they say you don't get caught in some high up minimum that's far away from the global minimum is because there aren't so many out there, especially when your model is large. Right? And there's a further discussion by Mr. Martin who suggests that it looks like a spin glass model, a spin glass funnel used in protein folding, and I haven't really appreciated that analogy. So the other method that came up is the idea of using the renormalization group. And what happened was Mehta and Schwab found an exact mapping between a Boltzmann machine and a kind of renormalization group calculation. Renormalization group calculations were used in physics to solve problems involving multiple length scales, essentially. So if you have a small model of interacting particles, then you combine them and sort of make bigger globs that interact slightly differently and so on. And if the interaction form is the same, you can repeat that process and ask, where does your model end up, right? And that turns out to give interesting properties. And it turns out that near phase transitions, these models are self-similar, so you can actually plot the trajectory and analyze the transition. And it's thought that similar effects might pertain here, which is in some sense you'll get self-similar models in certain cases, in which case you can analyze them. So then the idea is that, as you do coarse graining of particles into globs in renormalization group, the deep network actually does the same from layer to layer. You have a huge number of features, and the next feature coarse grains them and picks up something, and so on, and you go down. This just shows examples of their calculation on an icing model. And you're comparing it to a restricted Boltzmann machine. There's no major takeaway, I guess, except you have coarse grained features But I guess their main finding was the actual mapping, right? That there is an exact mapping between a restricted Boltzmann machine and a renormalization group calculation. So then we look at a third model, which was presented by Schwartz, Zeev, and Tishby in 2017. What they did was they analyzed the mutual information between the layers and the input and the layers and the output. Right? So looking at the bottom, I guess it's the number of bits of mutual information. And on the y-axis, we have the mutual information of any particular layer with the output. And the colors are the layers. And the reason you have many points is they did many different runs to get, reasonable statistics. So then what you see is, I guess maybe the movie might say it better. So you see these layers sort of move up as the information about the output increases. And then they start to drift left, which means they're losing information about the input, what is considered irrelevant information. So that was a fascinating finding, and they have some explanation of this process where initially they think it's a learning phase up to that point, where then it starts diffusing left slowly, right? And so they're able to explain why the diffusion works much better with deep layers, with many layers, because you have to diffuse less at each step, because you have many layers. So it's faster learning with many layers, which is observed sometimes. So it's a fascinating result. So again, you can see the sort of move up and to the left as the number of epochs go. They also point out that this is just the mean and the standard deviation of the weights. They point out that the weights are initially sort of, I guess smooth, and then later they become noisy, right? So there's an introduction of noise starting at about, 500 epochs or 300 epochs, and that sort of is part of the forgetting process of forgetting the inputs. Right? So it's a very appealing theory. And they construct some, I guess, compression metrics. The idea is that you learn first initially, and then you sort of compress your learning to reduce the number of bits. So that's fascinating. And with that, I'll end. statistical mechanics can still be useful. Would be fun to understand how it all works. Yeah?
Does the regularization parameter affect diffusion?
I don't believe so. I think they've tried models with regularization and not. And I don't think it does, yeah. Yeah.
Yeah, you said in one slide you avoid bad local minimum with a large network. I mean, do you mean like a very wide network or very deep network of layers?
Can you please repeat the question for the recording?
Yeah, so the question is whether when I say large networks, I mean deep networks or wide networks. And I think it's both. I mean, both work. I mean, if you have...
They're both different, right?
Yes, they are. If you have a large number of variables, I guess you don't run into these problems. So the variables can come from the width or the depth. But my guess is that there's probably some limiting cases, so I'll back off. I mean, if you have a single layer or something, there might be less than...
Or the number of nodes too in each layer, is that?
That's roughly the sense I got. That's why I used the word large rather than deep or wide. Yeah.
Is there work to apply convexification methods, maybe by using different kind of norms, convexify the energy landscape?
Wow. I mean, you want some complex energy landscape because you're building pretty complex models.
Right. It's just that in seismic, for example, in seismic methods, recently they've applied something based on optimal transport, like Wasserstein distance, using a different norm, convexify.
Okay. Yeah. It's what I'm not aware of. So. Thank you. Yeah.
Would you think that a simulated annealing algorithm would be a good solver for the weights?
I don't see why not. I mean, but stochastic gradient seems to be working, so I'm not sure how much better it will do. Because ultimately the thought is if you find the global minimum, you might be overlearning. So, you know.
I was just wondering if there's one of these problems that could be amenable to a quantum computing solver.
I'm sure someone will devise an algorithm. So.
Other questions?
Thank you.